Sorry to those on the recording. Okay, so yeah, so Model C minimizes mean squared error. The picture I want you to hold in your head is identical, really, to the one we had from last class, where we were moving around the intercept. But in this case, we're moving both the intercept and the slope. The steeper it is, the further out we go on this the slope figure. And we can make it very, very steep, but our error gets really wrong. So you can see the further we move out, the more error we have. But also, the flatter and then the more negative the slope becomes, the more wrong the model becomes. So there's somewhere in the middle that we need to pick for the slope. And thankfully, we can do this very nicely mathematically because we're using mean squared error. We can take a derivative of the thing and then maximize it like we do in econometrics. We can just find this mathematically really nicely. And it's not something we're doing in this class, but this is just an optimization problem. If you love that stuff, there's a whole sequence devoted to it, which you can take. But so that's what's going on behind the scenes. We're trying to pick the slope and the intercept that minimize the mean squared error jointly. So we're picking both at the same time. And our figure will look like this. Or it could. But whatever the case is, we're going to minimize our mean squared error. And we have computers to do it. So you don't have to do it by hand. When we started actually developing these techniques, we didn't have computers to do the calculations. So we didn't have digital computers to do them. But we did have people we called computers to run these operations, which I would not have loved that job. Okay, so this is a slope we have from the data, but the big question we're trying to answer is, this is just one sample. Like, we drew this sample, and it's the thing we're observing. But every time we draw a sample, we get a slightly different data set. So the question is this slope simply a result of this particular sample? Or does it, like, what's the probability it's actually telling us something about a relationship existing? So my question is, if the slope is actually 0, could we be seeing this? Like, is this consistent with no slope at all? Which would tell us that there isn't a relationship between wait times and minutes in the day, even though we're seeing it in our sample. These are the kinds of questions you're going to be asking in your projects. These are the kinds of research questions we ask really in any area of empirical research. Yeah, James?
Would the answer to that question be a calculation, or would it be based off like more qualitative analysis?
Yeah, so we're developing the machinery to be able to answer this quantitatively. Yeah, and the magic, it's not magic. The reason we can do it is because of the central limit theorem. If we didn't know the sampling distribution, we couldn't answer it with numbers. But because we know the sampling distribution from the central limit theorem, that allows us to make probabilistic claims. Okay, so to try to give you some visual intuition for the answer to my question, we see the relationship in the data, but fundamentally, every sample is random. To visualize this is the picture I want you to hold in your heads. I'm drawing 8 different samples from the same underlying distribution that I drew the original data set from. Remember, this is fake data. I control the underlying distribution, and I can draw it as many times as I like. Here I have 8 samples. Each one is coming from the same underlying population. And I'm going through with each model and fitting a statistical model to that data. And what you can see here is, most of them are positive. So horizontal axis is wait time, time of day. Vertical axis is wait time. What you can see is most of these samples, we see a positive relationship between the two variables. But not everyone. This first sample actually has a negative relationship. So simply because we see in the data that there's a positive relationship, it does not mean every time we take the sample, we would see that same positive relationship. We have sampling variability in our slope parameter, just like we do in everything else. And you're only going to see one of these, unless you run many studies. But in general, you're only going to see one. Any questions here? This is where I pose for the shocked look for the. My YouTube algorithm actually doesn't have a lot of that stuff, but for the thumbnail. Okay. Terrible joke. Let's move on. Forget I ever said that. So here, this is just 8 samples. My question for you, let's say, so I'm going to give you a figure on the next slide. I'm going to sample 1,000 times, run a statistical model on all 1,000 of those samples, and plot a histogram of the frequency of each slope parameter. So I'm going to, horizontal axis is going to be beta 1. It's going to be the slope parameter across 1,000 samples. Your job is to make a wild claim to the person next to you about the shape of that distribution, and then I'm going to show you what it looks like. Make a claim, make it wild, and then, I don't know how you do that. Maybe an exponential distribution, a censored distribution at 0. It'll take about a minute here. Make a claim, make it wild, and then also justify what you're saying. And then we'll plot it on screen. So you're saying most of these you think so? Oh yeah, because they're pretty small. Yeah. Yeah, so this is actually the short answer is even though they're very small, for sort of yeah, so if we round them, they will be yeah, we round them, they will be.
Yeah.
I'm not sure if this is okay. Someone want to make a wild guess? Someone other than James? If you all hold out, I'll go to James. Right.
Would it be like a bell curve, maybe centered over like 0.01 or something instead of 0?
Okay. So maybe not centered on 0,
Yeah.
but like a t distribution or a normal distribution centered on some number that's maybe slightly positive. Yeah. How many of you agree with Ryan? Hands up. So those of you who don't have your hands up, you had something else? Any other ideas? And the rest of you are just like not committing? Okay, I see you. Welcome back from spring break. So yeah, I agree with Ryan. So I'm going to plot 1,000 slope parameters. I actually did this. I collected 1,000 samples. I built 1,000 statistical models, took each one of the slope parameters, and plotted a histogram of those things. And it looks like this. And I think Ryan actually got this exactly right. So it's the sampling distribution is a t distribution, and it's centered on something that's small but not 0. So in this case, it's centered on 0.010, which turns out to be exactly the true slope that I used to generate this data. So what does this tell us? Does this look familiar? I mean, this looks identical in shape and form to what we saw with the intercept parameters. And we knew that from the central limit theorem. It turns out not only does the intercept parameter follow a normal a t distribution centered on the truth, but the slope parameter follows similar central tendencies. It's very unlikely, for the same reasons it was very unlikely for you to see a 1 when you take large samples of many dice. Any slope, for it to be very extreme, you have to have the data oriented in a very particular way. It's very difficult for you to get extreme slopes from data sets like this when an extreme slope doesn't exist. Extreme events are very unlikely and become increasingly unlikely when your sample size gets larger for the same reasons. There's more math to be done there if you're interested in it, but that's not for this class. I just need you to know the intuition. Okay, there's also a great question about the numbers here. These look like really small numbers. So like, we might have some questions about whether there actually is a slope, right? Like, the slope is really, really flat. Or like the relationship here is really, it's a very small number. Like the slope coefficient is, on average, between 0.01. But we can, using statistics, separate even small numbers from 0. And we can use the same approach that we've used in the past. The actual size of the number doesn't actually impact the kind of statistics that we can do. And the reason is because we can have sampling distributions which fall generally outside, or like don't overlap with 0 much. So let's be more specific about this. So these are some of the things we know, but we can also follow exactly the same process we did with our hypothesis testing, and then the hypothesis testing approach we applied to the intercept parameter. We can do all of that, but with slope parameters. So just like before, we don't observe all of the samples that I drew. Like I drew 1,000 of them, but in practice we only observe 1. So we see the sample, and we know the sampling distribution mathematically from the central limit theorem. So these are the two things we know, and this is enough for us to make claims. We need a null hypothesis. So let's say even though the sample the sample slope is very, very small, let's use a null hypothesis of 0. This is what we call the default null hypothesis, which is that there is no relationship between the two variables. If there's a slope of 0, that means there is no relationship. This is our default null hypothesis. This is really powerful when we talk about a null hypothesis in the context of univariate data. That's often very contrived, right? How do you pick the null hypothesis when you're testing means? Like, is it 7? Is it 8? How do we pick that number? It's pretty arbitrary. But when we talk about slopes, picking a null hypothesis is not arbitrary. In fact, the default null should be 0, right? That there is no relationship between the variables. So this is actually very, very well grounded. So we'll set the default null equal to 0, and then we'll center the sampling distribution on our null hypothesis, our sort of baseline guess. And every null hypothesis is truly a guess. It's just when we're thinking about relationships between variables, starting with no relationship is truly the right place to start. So then we center the sampling distribution on 0, and then we look at the area in the tails more extreme than our sample slope. We use the area in the tail above, in this case, but we also look at the area in the tail below, which sort of allows us to make claims about extremeness in both directions. Like, what's the probability of seeing something as extreme as what we do if the null hypothesis is true? That rhymes. Didn't intend that. All right, so this is our p-value. Just the area in the tail is more extreme than our sample mean. And this allows us to make claims even for small values, because the smallness is all relative to the size of the sampling distribution. The actual numbers themselves don't, the magnitude of the numbers doesn't actually matter. It's the relative size of our sample to the sampling distribution. You can eliminate all the numbers or multiply them by a million. Everything will look the same, just with different numbers. Okay, any questions here? James?
Are we still not right now concerned about the significance of?
So we're not going to make, in general in this class, and I would argue in science broadly, we should not be using rejection criteria. But we can talk about the p-values without talking about whether we accept or reject.
Okay.
So this is just a claim about the sort of consistency of the null hypothesis and and our sample. Does that answer your question?
Yeah.
Yeah, that was a really good one. What else? Okay, so the p-value is this measure of the surprisingness of our sample under the null hypothesis. Okay, this is the last, one of the last figures I want to show you before we start working with this stuff. Some people, I made this figure last semester, and students last semester, some of them loved it and some of them hated it. Let me walk you through with this polarizing figure. We'll show you. So this is one sample, and I built a statistical model through the sample. But then I also drew a bunch of samples under the null hypothesis and built sample slopes drawn from the null hypothesis, from the null distribution. So if the null hypothesis were true, we would be essentially picking one of these slopes in gray. So we'd be selecting one of these slopes if the null hypothesis were true. But I've also shown the model that we do see. And the question is, how surprising would it be if we picked this model from these gray ones? And that's essentially what the p-value is quantifying. Under the null hypothesis, we'd expect to see slopes that look like this. But what we're actually seeing is this red one. And from this figure, I think it should communicate to you that it would be very surprising if we drew the red one from the pile of gray ones. Do y'all love this figure? Most people say no. But I say yes, and I'm writing the slides, so it's staying in. Not quite a democracy, although mini-exam on Thursday, I think that is a democratic decision. All right, so nice. It looks unlikely to me. I think you all are probably tired of talking about wait times. Who cares? You want to talk about happiness scores? So I went out, I found this Gallup polling goes around and collects happiness scores from around the world. by country, and they do this every year. And then I've also merged it with GDP data. So we're going to hop over to exercise 4.1, and you can download the data sets if you like, but we're in a place in the course where we can work in notebooks. So here's exercise 4.1. We have, I think, quite a bit to do before the end of class, which is A-okay. I'm going to save a copy in Drive. Surprising, I know. And then I'm just going to load the data set. So this is life evaluation and GDP per capita. The World Happiness Report is put together by the Gallup World Poll. And then I also have GDP from the World Bank. I did a couple of things here. So this is loading the data set. I'm converting GDP into log GDP per capita, which makes it more standardized, like we've talked about with log. And then I'm just filtering for 2024. And this is what the data set looks like. So we have year, we have country, life evaluation, which goes from 0, I guess it goes from 0 to 10. And then I have GDP per capita and then log GDP per capita. All right, so the first thing to do, you're gonna work on this by yourself or with someone next to you, is just to set up a nice way of summarizing the data. This is classic part 2 exercises, just to get started thinking about the data. We'll take maybe 2 minutes here. All right, do you get something like this? SNS.scatterplot data, comma, x equals log GDP, y equals life evaluation. Okay, nice. So the second thing we're going to do is extend the core ideas we talked about at the end of 3.4. We were introducing model fitting at the end of that class. What we're doing here is introducing a predictor variable. So instead of just using the intercept, we're going to have an intercept plus, so our intercept, beta 0, plus slope parameter, beta 1. Should we walk through this together? My last class was really tired getting back from spring break. We just did all of this together. Do y'all want to do it together or in groups? Do you like the group work? Should we just do it together? Sure. Okay. It's easier for me. Maybe less educational, but we'll do it this once. Okay, so the first thing we're going to do is actually just fit the model. I'm giving you a bit of a hint here. What we're doing is we're just going to set model equal to something. So we're going to run a statistical model, but then save it as a variable called model. SMF, like we talked about last time, is the nickname for stats models formula.api, which is just the way of writing statistical models sort of in plain language. So this is smf.ols. OLS is just ordinary least squares, which is another name for the general linear model, essentially. They're basically synonyms. General linear model is just the more modern name for it. And then we're going to give it the y variable. So we have life evaluation, which is our y variable. It's on the vertical axis, like we've set up in our figure here. So we're trying to predict life evaluation using log GDP per capita. And then we're going to predict with log GDP per capita. So we have log GDP per capita. Okay, so this is our predictor variable, and this is our outcome variable. This tilde is basically stats model's formula language for an equals sign. And then we're just going to give it the data. So I think you can put data at the front or at the back. I think in the hint I put it at the back. And then we just apply fit to the thing. Maybe we actually have to put it on the back. I can't spell. Life evaluation, and then we run this. Dot fit. If we were to just print out model, so we print model, it gives us something that is not readable. It's this little like package of stuff that Python knows how to interpret, but we don't. So what I'm going to do is write out model.summary and print this out. It gives us this output that looks like this. I personally think this doesn't look very readable. It's not in sort of a standard format. So what you can do is put print around the thing, which will format it nicely. I think this is a lot easier to read. And this shows us a lot of things like we talked about last time. So there's a bunch of separate stuff. We don't really have time to talk through all the details here. There is an R squared, which some people care about. We'll talk about R squared later. We have an F statistic, which is important, but we're not going to talk about it in this class. And then some other measures of the model. The important stuff happens down here. So we have our coefficients and some other results. What we mainly focus on is that second part of the table. So we're just going to select, of the tables, we're going to select the second one, which we index by 1. So it's not 0, it's 1. Python indexes from 0. So here I just have the main part of the model summary that we usually care about, which is this stuff. So we have the intercept and the estimated coefficient for the intercept. Our beta 0 is this number. So this is negative 0.25. And then we can have find the rest of the statistics for the intercept term. So this is the standard error, which you remember was what we used to construct the sampling distribution given to us by the central limit theorem. So it's sort of the tightness of the sampling distribution around the truth. We also have our t-statistic, which we've talked about, but we're not going to spend a lot of emphasis on in this class. The t-statistic is mathematically what we call isomorphic with the p-value. If the t-statistic tells us something, the p-value will also tell us a similar thing. We have the p-value, which is the probability of seeing something as extreme as what we do, given the null hypothesis. And the null hypothesis in these models is always going to be 0. So the null hypothesis for the intercept is that there's no intercept, that it goes through 0. So the p-value here is telling us the intercept is not very far from 0. It's not very surprising to see an intercept this size, given no intercept is the truth. And then we also have a 95% confidence interval at the end. The last thing we have is the same statistical output, but for the slope coefficient. So this is log GDP per capita and how it relates to happiness score. This is the coefficient, so this is our estimated beta 1. This tells us every time we increase log GDP by 1, we increase happiness by 1.5, roughly. We also have our standard error. So this is, again, the sort of the size of the sampling distribution of the around the null. This is the t statistic. So how many standard errors away from the null hypothesis is the sample slope. And then we have the p-value, which here, this tells us the probability of seeing something as extreme as what we do, given no relationship between the variables, is essentially 0. So we could sample from the null distribution many, many times and still not see something this extreme. So this is strong evidence against the null hypothesis. We still have not made rejection decisions. We're not rejecting the null. All we're saying is this is the probability of seeing this given the null. And then here's our 95% confidence interval. Any questions here? All right, I love doing your work for you. Okay, so the second thing we're going to do is just visualize this model. I think we've used regplot before. It's essentially this, the same Seaborn syntax as you're familiar with. We can just really copy paste scatterplot, drop this in, and then replace this with regplot, and we get our nice little regplot, which is just a picture of the numbers we've shown here. I think you can also do LM plot, which is the more general version. Either way you do it, Seaborn handles this nicely. Same syntax with every figure we kind of draw. Okay, so then you can answer these questions. For the sake of time, I'm not going to do it. This is, what's the estimated slope beta 1? Is it positive or negative? Well, we got the estimate. It's like roughly 1.5, so it's definitely positive. What's the p-value on the slope? It's pretty close to 0. And what's the null hypothesis for this test? Tell your neighbor what the null hypothesis is for the statistical test by default in these models. I can almost guarantee you it's going to be on mini-exam 4. Maybe even mini-exam 3. It's 0. The test that's the default null hypothesis in our software, and really any software you run, will be 0. All right, the last thing we're going to do is make some predictions. We've gone slow, which is good, but we're going to speed run through a few things. Can I teach you some high school algebra? Is that a yes? So if we're trying to make predictions with our model, we've gone through and fitted our model. I'm wondering, on average, how many minutes do I have to wait if I go to the shop 100 minutes after they open? And the way we learn the prediction of the model is we just plug in an x value into the linear relationship. It's really not more complicated than that. But this is how we make predictions. So I'm just going to plug in 100 into my model, and that's going to give me a prediction of the wait time. If our model is correctly specified, this will give us the average wait time at 100 minutes. You plug it in this case, what's that, 5.4? And if we wanted, you can do this with a calculator. We're going to do it in Python in a second. If we wanted a different prediction, we just plug in a different x value. We do this in this exact same math in Intro Micro, if you were in that class with me. You also did this in high school. So we could do this in code, thankfully. It might be a little bit harder than a calculator because it's so simple. But we'll do more complicated things with this later. All right, so to get an estimate, there are more fancy ways to do this, but I want to show you the basics. So we fitted our model, which was above. So this is model. We just want to get the parameters. So the estimated beta 0 and estimated beta 1. So I'm going to say model.parameters, params, and this gives us this thing, which is just the estimated intercept and estimated log GDP. So those are the numbers. There are two of them, so I'm going to set beta 0, so B0, and B1 equal to the model parameters, which just defines B1 and B0 according to these two parameters. James?
And this is different than the estimated slope.
The estimated slope will be this thing. So the parameters are the estimated intercept and estimated slope.
Okay.
So we get B0 is our estimated intercept, and B1 is our estimated slope. And we can just print them out as we like. Okay. So I'm just going to set these B1 and B0. And then I'm just going to set up the equation for the line. So I want to predict the happiness score for countries with a log GDP per capita of 3. So I'm going to say x is equal to 3. And then I'm going to, we could set it equal to y hat, or we could just say B0. So write out the equation for the line. B0, then B1 times x. And this is going to give us the prediction for the happiness score of countries with a log GDP per capita of 3. So simple algebra from high school to give us a prediction. This may seem simple, but this is the kind of workhorse model that we actually use really in every area of empirical science. Yeah.
You said that basically by doing B0 plus B1 times x, you said that's the estimated what for, or can you re-explain like what that is?
Yeah, so the picture I want in your head is this thing. So we're plugging in the x value into the model to get the prediction.
And
Yeah.
the x value is 3.
In this case, the x value is 3.
Okay. And that gives you the version for that specific x value.
Yes, gives you the prediction for that specific x value.
And so are we gonna find a way to do it for all x values and plot that?
We can. Yeah, we're not going to do it this class, but that's not hard to do. In fact, actually, that's exactly this thing.
Oh, okay, that's all that is.
Yeah. But you can get specific numbers as a list. Okay, so that's for this one. I think we do have time. Let's take like 30 seconds here. I want you to construct the prediction at a GDP per capita of 2. We'll take like 30 seconds here. Look at the clock. Let's keep it snappy. Okay, someone help me out here. What's the number you got? 5.8. All we do is we plug in 4 instead of 3 in for x, and we get roughly 5.8. Any questions here? So, the last thing I want to talk about is the interpretation of this stuff. Here we have two different numbers, two different predictions. One is one horizontal unit higher than the other. And all we want to do is find the difference between those two horizontal values to measure the impact of moving one unit on the horizontal axis. So what happens when your log GDP per capita goes up by 1? How does your happiness change? Well, we can just take these two numbers and subtract one from the other. So I'm going to look at the impact of an increase in log GDP per capita of 1. So you're multiplying your income by 10. Multiplying your income by 10, what happens to your happiness? It goes up by 1.51. Does this number look familiar? This is exactly equal to the coefficient for the slope. That's what the coefficient is telling us. Every single unit increase on the horizontal axis is an increase on the vertical axis of this number. So you multiply your income by 10, happiness goes up by 1.5 on the scale. So that's the interpretation here. The slope of beta 1 in context. So for every, in this case, 1 log unit increase in x, y increases by 1.5. And then we would just adjust that according to a multiplicative scale. So every time you multiply your income by 10, we increase our happiness by 1.5. All right, so get that into Gradescope. I'll see you all on, I have one last question for you. Do you want to hold a review session tomorrow? My last class thought 5 o'clock would be a good time. What do you all think? Hands up for 5? Okay, let's go with 5 then. I won't record it. It'll be very similar to the demo that's on the course page. Yeah. Friday at 10:30 to 12:30. But we can schedule another one outside of